Hello there. Today we'll be doing moving average from data stream. Given a stream of integers in a window size, calculate the moving average of all integers in the sliding window. So here we have an example with moving average and four other functions called next. With the moving average function, we generate a, let's say, object with a window size of 3 where we can hold 3 items. The first item we input is a 1, the next item we input is a 10, and the third item we input is a 3. So the idea here is to keep a moving average and be able to return it immediately when we call next, as we see in this explanation. See, when we call next 1, we have 1 divided by 1. Next, we call next 10. We have 1 plus 10 divided by 2. And then next 3, we have 1 plus 10 plus 3 divided by 3. And we would get that average. And next, we would remove the 1 and add the 5 instead. And now we have a total of 6. So a simple way that let's to understand more about this problem is to read the moving average function. So initialize the object with the size of the window and double next. One question to clarify the problem would be, what would happen if we call a window size of 0? The problem of calling a window size of 0 is that we might divide by 0 because we have 0 items, and that would like create a divide by 0 error. So I would take that out of our possible inputs when we talk about the moving average. The window size, if it is a 0, we should just like throw an error, maybe like assert error, false, something of that nature, to make sure that, or a negative number. Let's say a negative, anything below 0 isn't, anything below 0 is bad. Okay, it's a bad input for a sliding window. We just cannot take care of that input. Now, should there be a maximum window size? I think as big as our numbers can get, I think that's fine. About the item, how big the item can it be negative, 0, 1? I think that should be possible. We should be able to take in a 1, 0, 1, 0, 1, negative 1, just anything of that nature. All types of numbers should be accepted. In this sense, the average would be 0. So, and we do have an edge case to make sure that we return 0, right? Okay, so because 0 is a different animal than most numbers, usually 1 and 0s. Okay, because in 1 and 0s they mean 1 means true and 0 means false in Python. Okay, let's run this. There's an indentation error, it looks like, because we have not filled in this. So we are ready to make some time and space complexity, like predictions. I think that comes from like a match. So one idea is that we use a O of n time, and how we do that is create a total item. So, and we add to that total, and with that we can divide by the number of items in our queue, and with that division we will be able to get our average by just adding one number. So let's say we had 1. Now we have 10, right? So we had 1 and now it's 11. 11 divided by 2, perfect, right? And then we have a 5, and then we can have that's a total of that's a 3, sorry. And we have a total of 14 divided by 3, and we just remove the last item and we insert a new item into our queue, and we can remove that item from our 14. So 14 minus 1 is 13, and then we add a new one, add 5, and then we have a total of 18, which is our number, 18 divided by 3. That way, we make it O of n operation by the number of however many next items there are. But in a sense, what we're doing here is returning O of 1 for every time we call the next function, and the O of 1 for moving average when generating the sliding window and the queue. So if n is size of a window, then O of 1, but n is number of next calls. And we use a space of O of n if, well, m actually, if m is the size of the window. So we do need to hold on to m items depending on size of the window. However big the window is going to be, we have to hold on to all those items because we have to be able to remove the correct item when the window is full, or otherwise we'll have an incorrect answer. So let's match. We're going to be doing a DQ to items, to add items, and we're going to have a total with a plan. What is our plan? Well, create a DQ, add items into DQ until window size. We have to create a DQ, create a total, create window size. Upon next call, return total divided by window size. If full window, if window size is full, then remove the leftmost item from total and add new value. And with that, we are done with this problem. Of course, we have not implemented anything. Let's do that. So we have a self.size equals size. We have to have a total, self.total equals 0. We also have to have a DQ. Of course, a DQ would require us to create a collections. And this is basically collections dot DQ. With that, we have completed step 1, and let's start adding items into our queue. So we have a value. So if DQ is equal to, if size of DQ, self dot DQ, we take the length of that, is equal to window size, so self dot size, then we need to remove DQ dot pop left. So we do a pop left and remove val. We have to remove this value. So we take from total. So total minus equals remove value. All right, and now we can insert a new item. So self.dq dot, well, push. Is it push? I'm not sure. Probably push. We're going to push this value into our DQ. We're going to add this to our total. And we're going to return our total divided by the number of items in our self.dq. And with that, we have completed the problem. Let's see if there are no syntax errors. And I don't think there are any. So let's just run one of these options here. So this is our review. As you can see, this video is getting pretty long, so we will be speeding this up. And let's do a print statement. I think a good idea would be to run the print statement inside. So we have an error. Okay, so yes, we cannot have that. We do not have a push function. I think it's append. Total. Oh, right. It has to be self.total. And we have another total that's I think we're good. Okay, it looks perfect. So that was what we wanted. And for our review process, and there is a edge case where we have no items, remember? Where the window size is less than 0. So if size is less than or equal to 0, then we just have to assert false. So suppose we run moving average at like 0. As you can see, we have asserted a false. That should not happen. All right. With that, we have taken care of that edge case. And lastly, there seems to be an edge case here with the 1s and negative 1s. So I think it should be fine if we go below, make sure we can divide by 0. I mean, not divide by 0 items, but like take 0 divided by total number of items. So just hanging around the negative 1 area. So it's perfectly fine. So 1, 0, 0, 1. Hey, wait a minute. So this should be 1. What's going on? It should be 1/3. Uh-oh, that's weird. Let's see what's going on. Oh, that makes sense. Yeah, that makes sense. So it had these 3 values. Now it has these 3 values. And then it has these 3 values. So it's perfectly right. And then we have one more 1 at the end. And then we have perfect. 0.33. Perfect. Yeah, looks good to me. And so now we can remove the print statements and go through. I think that specifically goes through the code exactly what happened. So we created a size window of 3. And so we added our first item in. We had a 1. So that's how we got our average of 1. Then we added a -1 in. So 1 plus -1 is 0. So we got an average of 0. 1 minus 1, 0. We got an average of 0. And -1, 0, 1, 0. And then 0, 1, -1, 0. And then 1, -1, 1, which is these last 3. And we got a 0.033. So that's perfect. Evaluates. So the O of what we had to do was O of n, if n being the number of next calls. Otherwise, it's O of 1, because this is an O of 1 operation to call next. And the O of m, if m being the window size, because we do need to save all the items in our window. It wouldn't work otherwise. With that, hopefully you saw that. Well, you see it now, so yes. With that, we have completed this problem. If you enjoyed this video, please like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I will see you in the next one.